Now I'd like to talk about hazard avoidance and mitigation associated with volcanic activity. Here you see in the upper left-hand diagram Mount St. Helens before it blew its stack in 1980. You see in the lower right the active volcano sending up its spew of material while it was erupting. And then on the lower left, you see what's left of Mount St. Helens, having basically ejected the upper 1/3 of the mountain itself. So in this discussion, I want to talk about the implications of this kind of activity and the damage that it can generate and how we go about identifying, avoiding, and mitigating that damage through landscape planning. This map shows volcanic activity in the world, and you can see that generally speaking, this volcanic activity tends to follow tectonic zones between continental plates. For example, all the way up and down South America, the west coast of South America through Central America and North America, you see these red triangles which represent volcanic activity extending up and down the west coast. This is where various plates underneath of the Pacific Ocean intersect plates with the North American plate and plates in South America. And you can see that this is what we call the Cordilleran Belt. It extends over around through the panhandle of Alaska over towards Japan and down through Japan along the Asiatic coast. Volcanic activity in the Pacific Northwest is quite pronounced. Most of the volcanic activity in the United States is located in the western part of the country, and particularly on the west coast. Potential damage that's associated with volcanic activity can involve the eruption-related earthquake itself. That is what happens when Mount St. Helens actually blows its top. Direct blasts, that is the material that is spewed out during the blast itself. Tephra, this is blasted rock debris coming out. Volcanic gas emissions, you can see this is on Mount St. Helens actually, and it's considerably downslope of the area that actually erupted. You can see that the needles from the vegetation are all removed. This was an area where volcanic gas was emitted from the eruption itself and flowed downhill, damaging vegetation. Here we see in Hawaii lava flows coming out of an eruption of a continuous flow from a volcano in Hawaii moving across the landscape. We also can see oftentimes associated with the blast itself, debris avalanches and landslides in adjacent landscapes where for one reason or another, principally because the ground has been shaken quite significantly by the volcanic activity, we have slope failure and landslides associated with the occurrence of the movement of the volcanic activity. Tsunamis, these are tidal waves associated especially with underwater volcanoes occurring especially in the Pacific Ocean. And the pyroclastic flow, this is the material that's blasted directly out of the landscape, and it flows across the surface of the surrounding landscape. Something called lahar, or a mud flow, often accompanies the aftermath of explosion as mud flows begin to stream down the mountainside itself, and we can see that those mud flows can be quite significant. Land subsidence can be a pretty significant hazard. In this case, we see the Leaning Tower of Pisa in Italy, and the Leaning Tower of Pisa is leaning because it has It's in a zone that has had excessive groundwater pumping. The implications that this has, it can be shown in the diagrams underneath of, in the center, where a well has been sunk into an aquifer, and that aquifer has been pumped such that the pressure in the aquifer has declined, causing a concavity in the surface of the landscape. And that concavity then is what is causing the leaning tower of Pisa to lean. It is the collapsing of the underground surface associated with removal of groundwater through pumping in aquifers underneath the landscape that is supporting the tower. We can talk about excessive pumping in the diagram on the lower right. We see an area that is pumping groundwater, creating then a depression, a new depression in the landscape that we see in the lower right-hand portion of the image. Here we can see in Wilcox, Arizona, between 2006 and 2015, these are areas of land subsidence. And you can see in the legend of the map that the level of subsidence has gone from 0.4 inches over the 9-year period to as much as 15.7 inches in nine years due to groundwater pumping. So essentially what's going on here is development is occurring in the Wilcox area. To support the development, they are mining groundwater from underlying aquifers. In mining aquifer, they are dewatering the aquifer, reducing its hydrostatic pressure, causing the surface land to subside in elevation. We also can see land subsidence associated with deep shaft mining, especially coal mining, which often is a subterranean mining operation where coal is removed, and in removing the coal, the support structures for maintaining overburden, and especially the surface of the earth, are diminished. And as a result, a trough emerges, or holes emerge, where the overburden is no longer able to be supported because of the removal of the coal from the underlying area. This is exactly the same thing that's happening when groundwater is removed. The groundwater has a certain hydrostatic pressure. When the groundwater is removed, that hydrostatic pressure is diminished. Here, the in-place coal supports the land surface. When that coal is removed, the land surface no longer has the support and it sinks. Another form of land subsidence is called sinkholes. Sinkholes occur in something called karst topographic conditions. A karst topographic condition is a limestone type landscape. Typically, that limestone landscape is heavily fractured through tectonic activity. And as a result, when surface water seeps down through soil and finds its way into cracks and fissures, the surface water begins to dissolve the limestone. It makes the fissures and cracks larger in size, creating then caverns. And the caverns, if they are dewatered, the caverns lose their ability to support overburden. And we have the evolution then of what are called sinkholes, where the land simply collapses because the underlying limestone material has been dissolved as water is moving through cracks and fissures in the underlying limestone. We can see in the diagram on the lower right what's called a solution cavity in a highway cut through limestone, where we can see that the water has entered the limestone, dissolved the limestone, and created a clear passage for water to move into and down through the underlying landscape. In the upper right diagram, we can see sinkholes in the landscape. These dark areas are sinkholes. Water then gets into these sinkholes, it gathers in these sinkholes, and it moves down into underlying fissures and opens up caverns in the underlying landscape. And over time, we can see the evolution, the devolution, really, of a limestone plateau into a series of mesas where the entire landscape has collapsed through the process of sinkhole formation and collapse over time. Yeah, this in the upper left diagram and lower left diagram are from Kentucky. This is a limestone landscape where we can see a number of sinkholes that exist in the landscape. You can see that they're all essentially at the bottom of depressions because the sinkholes go down and join underwater caverns, uh, underground caverns created by the dissolution of limestone, creating this mock landscape that creates zones of weakness. We see on the right-hand side, we see these fractures in the limestone formation itself that permit water to get into the limestone. Once the water gets into the limestone, it dissolves the limestone and begins to create these large sinkholes. Some of these sinkholes can be quite significant in size. We can see these are sinkholes in Hawaii, in limestone landscape in Hawaii, and we can see that the sinkholes are quite large in spatial extent, large enough that you can build tourism facilities to accommodate people wanting to visit these sinkholes. Here is an image of a sinkhole, and you can see the sunlight coming in from the surface where the water has gotten into the sinkhole from the surface. This has a significant impact on the stability of the land surface. And so this sequence of diagrams on the right hand shows the evolution of these sinkholes over time and shows the upper left hand diagram A, shows a house built over top of karst topography. This is all limestone landscape, and there are underlying caverns filled with water. And as fractures occur in the limestone itself, those fractures fill up with water, and eventually they dissolve the limestone, creating underground caverns, and the surface of the earth starts to collapse. And over time, then you see the collapsing of this surface and the destruction of the house as it literally falls into the sinkhole over time. So sinkholes can be a significant damage creating hazard in the landscape. Here we see a sinkhole in Florida. And Florida is basically a limestone reef. So the entirety of Florida is subject to sinkhole development. And here we see a sinkhole that is opened up. And these sinkholes tend to open up quite rapidly because it's a gradual process of dissolution of the underlying limestone. And eventually, enough limestone is dissolved such that the cavern can no longer support itself and it collapses. Typically, it collapses in this circular fashion. This map shows all of the reported sinkholes since 1954 in Florida, and you can see that they are particularly intensive on the northwest coast of the Caribbean side of the peninsula. The reason there are so many sinkholes there is because millions and millions of years ago, there was a meteorite that crashed into the Gulf of Mexico, and it created extensive fracturing of the Florida Panhandle, and all of the sinkholes that you see along the west shore of Florida are a result of water getting into the fracture zones created by the meteorite crashing into the Gulf of Mexico. Here we can see some examples of sinkholes, some of them being quite small in scale, with the sinkhole that I showed you here. Some of them being quite deep. We can see cars falling into the sinkhole. We can see houses falling into the sinkhole. Sinkholes are active in Minnesota landscape, down in the southeastern portion of Minnesota, where we have an underlying limestone-like landscape that's not very deeply covered with overburden. And we have a number of sinkholes that exist in this landscape, and the landscape is quite susceptible to sinkhole damage. It's what we call an active karst zone, where water is seeping into the underlying limestone formations, creating these underground caverns, and over time they have a tendency to collapse.